Good evening. I'm Saurav Mishra, a PhD student at the Artificial Intelligence and Robotics Lab, Department of Aerospace Engineering, Indian Institute of Science. I'm pursuing my PhD under the guidance of Professor Suresh Sundaram. My research interests include multi-level learning, continual learning, brain-inspired computation like spiking networks, and computer vision. At AIRL Lab, we also look into robotics, reinforcement learning, and control applications. We thank IEEE ICASSP for giving us this opportunity to present our work. Our work is titled A Memory-Free Evolving Bipolar Neural Network for Efficient Multi-Level Stream Learning, and this is an outline of the presentation. We start with the motivation and objectives of the research. We then look at the existing methods in literature for lifelong multi-level learning. We then propose the EBN-MSL architecture, followed by the experimental settings and the results. We end with conclusions and future work. In the real world, data is often associated with multiple labels, such as the show can fall into multiple genres, such as science fiction, kids entertainment, and action. And these labels can increase with time, such as the number of COVID-19 variants recently. This motivates us to look into lifelong multi-label learning problems, which have the following objectives. Models should be able to learn from a stream of samples without forgetting the patterns they have seen previously, and in doing so, they should not utilize any samples stored from the past. In addition, we have the assumption that new labels might appear over time, however, the old ones will stay unchanged. Continual learning and multi-level learning have been addressed separately in the literature, while continual learning methods deal with simple multi-class setup and incremental arrival of data. Methods for multi-level learning require the entire dataset to be present beforehand. Also, the multi-class setup has much less imbalance compared to the multi-level setup, and we also impose the constraint of having no memory from previous tasks. Along these lines, there are two methods, deep streaming label learning, DSLL, and continual interactive feature distillation, CIFDM, which are architecture-based methods for lifelong multi-level learning. Both these methods use knowledge distillation for transferring knowledge between models trained on subsequent tasks. DSLL addresses a simple setup where only the labels increase with time or tasks, whereas CIFDM addresses a more challenging setup where both the samples and labels evolve with tasks. However, these methods are sensitive to imbalance. This slide describes our proposed architecture, EBN-MSL, which stands for Evolving Bipolar Network for Multi-Level Stream Learning. The architecture is shown here on the top left of the figure. It has two parallel layers, one positive and one negative. We train the model in two setups. The first setup, shown in the middle row, denotes sequential learning without model adaptation, or SEA star, where we train an individual model on each task and finally combine them for evaluation into a bigger model. The final setup is known as the sequential learning with model adaptation, which is shown in the figure below, in the bottom row that is. So here a single model is grown as tasks proceed to accommodate the newly arriving classes, and the parameters of the model trained on the previous tasks are copied over, and the larger model is trained on the current task. These models are trained in a maximum margin framework using loss functions shown in equations 1 and 2. Here, B is a hyperparameter that can be tuned, and it controls the margin between the positive and negative predictions from the network. The inference happens in a manner shown on the top right by comparing the predictions y plus and y minus from the model. This slide shows the experimental settings. We follow the same experimental settings as in the CIFDM paper, where each task in training consists of new samples and new labels, Whereas for testing, we use all the samples in all the tasks. In the individual mode of testing, we use only the labels seen in the current task. However, in the combined mode of testing, we use all the labels seen till the current task. We use 6 datasets and divide them each into 3 tasks as shown in the table below. And the third column here denotes the number of samples in every task that are not associated with the corresponding labels. The seen dataset is seen to have more than 50% such samples in every task. And we use the macro averaged precision, recall F1, average precision and area under curve as the metrics for evaluation. So this table here shows the results of our model compared against CIFTM in the combined evaluation mode. The seen dataset is found to give the maximum improvement of around zero point 0.4 for macro averaged F1, around 0.5 for average precision, and around 0.39 for area under the curve. It is also observed that EBN-MSL models consistently outperform CIFTM, and in the SEA star setup, they yield better average precision and area under the curve values than the SEA setup. Ablation studies show that the loss function L2 is less sensitive to changes in the margin parameter B, and that the combination L2 and B is equals to 1 work well for most of the data sets. Finally, we see that EBN-MSL is better at handling imbalance due to its maximum margin framework of training, and it consistently outperforms CIFTM. However, in the limit of large label spaces, the architecture growth of EBN-MSL can become a computational challenge. This will be one of the directions to explore in our future work. In addition, there is a trend of decreasing performance across tasks. This happens because EBN-MSL does not utilize any knowledge distillation between models trained on subsequent tasks. This will be another direction for future study. So that's all from my side for the presentation. Thank you for going through the presentation and have a nice day.